So, hello everyone. I'll be talking to you about something called knowledge graphs and semantic reasoners. So, let's get to it. First of all, I'm going to present myself. Well, my name is Alejandro León Escalera. I'm from Mexico, but I go by Alex. So, I've been working with tech for about 10 years. Started as a web developer for e-commerce websites. Then I joined Accenture, where I started to focus more on the front end of web development and for companies like Marriott, etc. Then I started going more into the realm of a full stack developer with serverless framework, with AWS, etc. And nowadays, I work as an architect with many aspects, with DevOps, with front end still, with microservices, and recently with this topic that is semantic reasoners, knowledge graphs, graph databases, etc. So, I want to start, well, we'll go through concepts. That's the main, the main thing of this talk. A couple of use cases and something called rhythm that we'll see at some point. That's also kind of the reason of how I got into this. And yeah, let's get started. Well, some references and questions. So, concepts. Let's start from the top. AI. So, a lot of people, when they say AI, they think immediately machine learning, but AI is more, encompass a lot more. I like this quote from Paul Daugherty, who is our CTIO, our Chief of Technology and Innovation in Accenture. He says that systems that extend human capability by sensing, comprehending, acting, and learning. The piece about extending human capabilities is really important. For those who joined earlier the talk with Matt and Eric Motasedi, they were mentioning about those dystopian scenarios, etc. We don't want to look at those. We don't want to look into a place that artificial intelligence kind of replaces humans. We want to work together with that. We want to enhance our capabilities and, in any case, work better in human interactions via AI. So, here are a couple of, well, like 5 things that you can find inside AI. It's not limited to this, but there's things that you might hear about, like machine learning, which is something that you hear a lot about. We also have sensors, because sensors give us input about information of the world, just like humans. Our eyes, our ears, can be a camera, a microphone, and even further, like radars or LiDAR. We also have robotics. Well, we try to emulate things like a person walking or moving around, or even things like drones that fly around, or other types of drones that go inside water. Then we have natural language processing, which is, well, the main means of our communication, of how we understand ourselves. And also, the realm that we are going to be focusing mainly is knowledge representation and reasoning. So, as I said, we're going to be focusing on that, and a little bit on natural language processing will be included in here. So, first of all, semantics. Semantics is a branch of linguistics and logic that is concerned with meaning. So, when you hear semantics, it's meaning of stuff. Okay? So, there is something in our brain called the semantic memory. That is a long-term memory where you store information as is, facts, like cold, hard facts, like the sky is blue, for example. There's another piece called episodic memory, which is more concerned with emotion and experience. Semantic memory is not concerned with that, but they are connected. So as I was saying, semantic memory is indisputable facts. How do you obtain them? Well, you can obtain them by just information. For example, here, the capital of Namibia is Windhoek. I hope I'm pronouncing it right. I've never been there. I haven't even seen photos. I just Googled it directly, and for me, this is just information. But it's, to a certain extent, certain knowledge, and is located right now in my semantic memory. But there's also reinforcement from episodic memory. When something happens to you, like you touch an iron and you burn yourself, it's a painful experience, so it gets into your head that when you touch an iron that's hot or something that's really hot that's a metal, you can burn yourself. It becomes your semantic memory. Sometimes reinforcement is like immediate, like that, and sometimes reinforcement takes repetition. So now let's move to knowledge. So a simple definition of knowledge here. From here, the important pieces are the experience and association. Experience is just what I told you right now from episodes, but association, that's a really important point with knowledge. Why is that? Because by itself, data is isolated. If I tell you just like blue, you say like, uh-huh, what about that? Well, sky. Okay, you might say, oh, he might be talking about the sky is blue. Yeah, so we have a relationship. In there, we have association. So it becomes certain information or knowledge that has meaning. So you also can have concepts that are connected, but inside a specific domain. So for example, if I tell you a parent has 2 children, okay, you might think, yeah, like you think of a man that has like a daughter and a son. But what about if I'm in a structured data topic? Then you might think of binary trees. So that depends on the context. So another important piece of knowledge is the context. And then a sequence of those maps. So we not only think like in representations, but we think in a timely manner. So if you have a sequence of different maps, then that can really represent certain knowledge of events through time, and we're going to see it in a moment. So knowledge is best represented by linking concepts. Let me show you. Just what we had previously. Windhoek is the capital of Namibia. Okay, that seems like very straightforward. What about the other one? Okay, let's say first, if you touch an object, that's an iron, and that object, the iron, is in a state that is hot, and you're using your finger, that's kind of a first state. Then you represent kind of the consequence. Your finger is burnt, and your perception is pain. So these 2 ways are representing knowledge via certain concept maps. So now, how do we store that? Relational databases, well, they convey their main meaning through the name of the table. Name of the table being I don't know, students, professors, universities. So, okay. However, relationships are not the center of that. Tables are the main focus. Relationships come as a second thing in relational databases, even if they're called relational. So you have to compute those relationships most of the times. And when there are relationships like many to many, etc., then you have to create separate tables or do some extra processing. And it starts becoming a little bit crumbled. Joins. Joins in a very big database are expensive, really, really expensive. So you say like, oh yeah, I want this type of information, etc. So you start doing some joins here and there, and then you have either a big structure or I don't know, some views in there, which are expensive to process. Now, what about the schema? SQL has a very strict schema. So let's say that, yeah, you have already your table with your information, and you say, I need to add or remove this column to this table. So you can do it if it is like just a column like that, but what about if it is a foreign key? Or if you're removing it, or you have to split that, and those are foreign keys, then it becomes a mess. So it's not really flexible for that. So for example, let's take back the example of the capital and the country. I may have something that's called cities and something that's called countries. Why are they not in the same table? Well, because if I were to create another table that is cities that I visit, then I wouldn't be able. I need to split it. Okay, they're split. But cities by itself, it conveys you that, yeah, name Windhoek, in which country is it? In country 147. What's that? Nothing. So you have to make that relationship, and that's something that comes at a cost, performance cost. So in the end, no, it's not a good idea to use SQL to represent knowledge. NoSQL databases, well, in first place, they were not created with that in mind. They're like more document-wise, where you have a certain structure already, a certain contract already preset. So key-value pairs, well, they don't really represent a relationship other than the key and the value itself. So, and maps, well, require interpretation on what are you mapping. Let's see the example below. So in here, we have country, Namibia, capital, Windhoek. Yeah, it seems like a relationship, but to us humans, because we are interpreting it. If we don't tell the computer explicitly what to expect, like we're expecting country and we're expecting capital as keys, then, and what does that mean? Then it's not easy to make that relationship right away. So you have to kind of have a contract really well predefined. And a map, well, it's the same thing. I mean, for a computer, the thing name doesn't mean anything until you tell it what to do with it. So no, better not use that. Graph databases, well, I mean, we've been using graphs until now, so they're based on graph theory. In here, you're going to see that the relationships are first-class citizens. They represent exactly what you want. They are as important as the information in the concepts themselves. They convey that meaning by self-definition, relationships. So giving an example of a very common database right now that is called graph database, that is called Neo4j. The only constraint you have when creating data inside Neo4j is that a relationship needs to connect either one or two nodes. What I mean by that is that it can connect the same node, or it has to connect two different nodes. So that's the only constraint. Aside from that, anything else can be done. So yeah, when I was saying schema lists, so there's no constraint about, I don't know, how foreign keys work, if they exist here or exist there. So going back to that example, yeah, you have this as, let's say, to a certain state of your graph database, but you can add more relationships as you go. There's no constraint. You can just add relationships. Oh, we have this new requirement to add this type of information. Yeah, just make a relationship. Or this connection doesn't work, delete that relationship, disconnect the nodes. And there's not going to be anything because each node by itself contains a concept. Each relationship by itself connects concepts. So it's really flexible on that matter. And knowledge, well, knowledge is something that is changing all the time. Knowledge from what we know right now will be different from what we know 5 years. Maybe not too different, but there will be advanced in certain things. So you need that type of flexibility to be able to change and reconnect things or remove connections. So, yep, let's use graph databases. Now, I want to talk to you about truly semantic data, because having a graph database like that doesn't mean that it's truly semantic. You'll see why. OK, we have this example. Arthur lives in Leeds. Leeds is a city located in England. Plain straightforward. If I ask you, does Arthur live in England? As a human, you would say, yes. It's, well, it's evident. A machine, what would reply? Either that, or no, or I don't know, but it wouldn't reply yes. Why? At no point I told the machine that Arthur is living in England. I told that Arthur lives in Leeds. And the machine understands England, understands Leeds, understands the relationship between the immediate nodes, but doesn't understand directly like the transition of the information. So, OK, let's do something. Arthur lives in England. Yeah, he will say yes. OK, Arthur is not the only person in Leeds. Amelia lives in Leeds as well. OK, so let's connect that. But then Oscar as well. Oh my God, let's connect. Noah, let's connect. So I have to do that for everyone? What about this? Do I need to connect everyone to Europe? No, because that's not how the human brain works. So let's go to the basic example. We just need to connect who lives in Leeds. And what we do is we create a rule. In this case, this is just an example, and this is pseudocode, but it's the idea behind that rule. If A lives in B, and B is located in C, that hops thing means that it's not, if you find located, kind of a recursive rule for located in, then you can infer that A lives in C. So we ask again the machine, does Arthur live in England? Well, it runs that rule and says, yes. Does Amelia live in England? Yes. Does Oscar live in Europe? Well, we have that 2 hops, that recursive rule, so yes, as well. So how do you get truly semantic data? You have a graph database, okay? Then you have a set of rules, which is called ontology. I'll explain in the next slide. And you have the so-called reasoning engine. So this definition is not mine. It's from a guy called Jesus Barraza. He's a PhD. He has a PhD on data information, I think it is, or computer science. Yep. He did his thesis in semantics and in graph data. Also, he worked in a company called Ontology Systems for 7 years, and nowadays he's the Neo4j Telecom's global lead. So you can imagine that this guy has a lot of knowledge on semantics and on ontologies. So, an ontology. Ontology is simply a vocabulary, a schema, a rule set, something that defines some rules of how to act upon data. Why do we use them? Well, several reasons. First of all, you need to let know your machine how to interpret information, just like we did earlier. You need to let know, with these rules, you can obtain these results, something that the machine can understand. And actually, that's how our brain understands it. It's kind of like, people say like, yeah, it's logical. Well, inferences are logical. It's usually what you do. You can make domain assumptions explicit. So what's this? Let's say, for example, we have a certain domain, and we have, I don't know, maybe a pharmacy industry, and we have data about that, compounds, certain drugs, what they're made of. So with an ontology, you can create certain rules that are specific to domains, and the rules are going to make it more explicit. It's going to help you understand, even you or your machine, how the domain is set, how the domain is going to interpret certain data. They separate the domain knowledge from the operational logic. So the domain knowledge is your data itself. But as we said, we cannot be connecting everything with everything because we would never end. Then you have to disconnect it, you have to move here, etc. No. Then you set operational logic that most likely will be inference rules. In that way, not only via the data itself, like the hard data in there, the machine is going to know how to find certain things. Via the ontology, it's also going to know how to operate through certain things, like people living in Europe just by going like 2 hops from the city to the country to the continent. Also, data sharing can be achieved via ontologies. So what happens here? Let's go back to the pharmacy industry. There might be laboratory A, laboratory B. What happens is that they have certain formulas, they have certain compounds, etc. There's some drugs that have the same formula, but for different laboratories. What if there's a hospital that needs to check information from both? Do I need to subscribe to your specific contract and your other specific contract? They're the same thing. If you prepare an ontology over that knowledge, then you can just make your information comply with that ontology, and it's gonna not only be able to check the data, to retrieve the data, but also go through that data and find out if there is any more information. Like if you found certain relationships from laboratory A, but then you're gonna find some other information from laboratory B and make your own resulting graph of knowledge. So that can be achieved by ontologies. And also, it helps you analyze the domain logic. Kind of the same thing. You don't need to go through the data itself. You just go through ontologies to understand exactly what's available. And then everything that is complying with that ontology, you will be able to pull that information in a transparent way. You don't have to care about if it's lab A or lab B, other than the tag itself. But that's going to be transparent. And as I was saying, you can also make a summation of the information that are in A plus what's in B. So just to make some other examples of ontology rules, not limited to, this is more like inference rules, which are some of the main ones, but an ontology can have as many rules as you need to. Actually, coming up with an ontology is very, very difficult. You need to know your specific domain real well. So you can see like the transitive rule that we had there, reflective rule, inheritance. But there are other things. For example, there's this thing called the semantic web that it's still there. It started as an idea from Tim Berners-Lee that we should share information in us with a certain tags so that the machines, so computers, understood the information in the web in a way that you would understand concepts as a human. So instead of going through all the information and parsing, you annotate the data on the web with certain ontologies, with certain rules, and then you make that available. It's out there. There are still people looking into this, but it's really difficult to come to like a whole convention for on internet. But it's worked well on certain specific places, like pharmacy or even governments, where they set up their information with existing ontologies. They don't have to go and create their own ontology. Some ontologies already exist. And it has worked well to share information among different entities inside a certain domain. So then comes the semantic reasoner. A semantic reasoner, the only thing that does is it's an algorithm that goes through your ontology, through your data, and infer consequences of the data, finding out new data, maybe removing at some point, at some level, also validating that the data is correct. So there are certain domains that you're going to want to have specific constraints to what you're going to do. And that's a per domain thing, not out of the box. For example, I was saying that Neo4j has no constraints. Well, you're going to want, if you're, I don't know, in the entertainment industry, you're going to want to have certain specific rules, usually called business rules. You can take that information from there, set it as an ontology, and then run your data through that. And if it finds something that is not correctly related to something else, etc., it's going to throw an error. Actually, there are some, in that realm of semantic web, there's this semantic reasoner called Protege. So I think it was made by Stanford, or Oxford, can't remember correctly. But the thing is that they have their own rules that they run ontologies through. There are some ontologies in semantic web, as I was saying, called RDFS, or called OWL, called SKOS. But independently of that, they're just simply algorithms that run those ontologies. They run it against your data in there. And if there is some error, they're going to say, hey, this is not OK. So here's a problem. You said that your information should follow this rule, and it's not following, so it's not valid. But in the end, it's just a computer program. So putting that together with the definition that we saw 2 slides ago, we have data. Let's take another example. Mark is a sibling of Mary. Then we have our ontology. We have in here, we take a reflective rule. If A is sibling of B, B is sibling of A. Yeah, so makes sense. We run that through a semantic reasoner. That, by the way, they can be called reasoning engine, rules engine, reasoner. There are many ways, even inference engines sometimes. We can find new data. And we didn't have to explicitly tell that to the knowledge graph. It's something that it came up with. So let's move first to a couple of use cases. Google Semantic Search. It's been out there for a while already. They have their own knowledge graph. So what they do is they take your search and they try to find relationships according to certain keywords. So they just don't parse the search that you have and say, OK, I have this keyword, I have this other keyword, and they try to search it in the web like that. No, they take them as concepts, and they already have prepared a graph with an ontology behind the scenes, and they say, yeah, it's connected with all these things, and sometimes even it's not connected, but they can do some, for example, page rank on those things to have weights on specific relationships. And that determines the quality of your results. So, for example, if I say, who is person X in Google search? If I were to parse it as a keyword by keyword, I would say like, yeah, who and is. I'm not looking for who, I'm not looking for is. I'm looking for a person, and the fact that I have who is a concept that is telling you he's asking a question. He wants to know about a specific person. So it needs to be able to understand that. And if you run that through a graph that's correctly connected with the verb is, with the argument who, and understands that, OK, it's connected because that's a question about a person, then it's going to understand that's an inquiry and give you information. And we've all seen this for a while now. You can see here, well, it's a little small, but you have seen how it is. The query is, who is Benedict Cumberbatch? You don't see only results. You see like his bio card, here and here. You see photos, but you also see top stories. If I were searching for, I don't know, laser pointers, I wouldn't see top stories. It's not relevant for that topic. But since you know exactly you're talking about a personality here, most likely there are going to be news about that personality. So that's something that might be a connection. I don't know. That's, for example, if you have your graph database and you have Benedict Cumberbatch, you have like, he's a personality. Personality is related to news. OK, it's a distance of 2. If I'm talking about this thing, it might be laser pointer, then like, I don't know, 13 hops to get to something that's related to news. It's not relevant. So you can know if something is relevant via hops, or maybe you can put some kind of weight in there, but it's all driven by those relationships on how your data is connected. Same thing here. There are quotes. Obviously, since he's an actor, he has movies and TV, and people also search for. So you can see that this one, especially, it's telling you that usually people that search for this, then we found out that they search for this other thing, so let's connect it, and then It can be as well weighted so that you know who are the people that are mostly searched when you did like given that you did that for person A. And, well, usually they're related people, his spouse, co-actors for a program, for movies, etc. But all these things, like you see here, are driven by a knowledge graph. Well, by a semantic search. Okay? So now, another use case, and why to use it, is to enhance machine learning training models. I'll speed up a bit. So the idea is that you can get connected features even further than just getting features and use that as input to your models. So you can do feature selection. Instead of running through all your data, you can just get a subset of the data and say, yeah, this is a connected subgraph that because of this rule and this rule, it's important to this scenario. So yeah, then with that you can run feature extraction. So it's not only about the data itself, the concepts, it's also about how they are connecting with each other. There's really meaningful information within the connection. So you do some kind of, well, parsing of that data. You change it to tabular format, but you have more information that you will usually if you had only like specific tabular data to start with. Or even feature engineering. You can use ontologies or something that we call graph algorithms that are among the same realm to find out new connections first, or even new data, as you can see in the purple ones, so that then that will enrich your training data as more specific, well, as something that's more specific to your domain. This is taken from Amy Hodler. She made this presentation. She's the managing director from Neo4j. And she also wrote a book about graph algorithms. So this kind of a good way that you can mix machine learning with semantic reasoners and knowledge graphs. And yeah, finally, I want to talk about rhythm. This is the whole. This is why we started checking on semantic. So Rhythm is an umbrella for distinct AI-driven solutions. It's a platform that we're creating with the idea of simply enhancing human capabilities in different industries. Depending on the industry is how we want to enhance. There's this specific piece that's called Rhythm Linguist that, as the name says it, is related to conversations. So it processes a human conversation via different neural networks, via some other things, etc. But the important point to this presentation is that they produce a semantic representation. So here you have this. Usually you have, let's say, speech to text. The product is text. No, this doesn't do that. This takes human conversation, runs it through some processes, AI processes. It produces a semantic map. Why is this important? Because it doesn't matter how you say things. I'm going to give this talk again in Chicago next week. Most likely, if they said word by word, are they in the same talk? No. But are they the same concepts? Yes. So we don't care really on the produced text, on the literal speech. We care about what's it about, the concepts. And then with that, we can do things like check if in a certain domain, let's say hospitality, is that an opportunity to act upon? It might be. It might be a customer requesting for towels or something. And that you can send it via different interfaces, earpieces, perhaps a radio, or a computer or a smartphone. And this small piece below here, we called it the semantic memory, which is our complete knowledge graph plus reasoning engine and ontologies. The semantic memory is based on the concept of frame semantics, which is something which means that you cannot understand one thing without having a frame of all that explains all the connected meanings of other things. As I was saying at the beginning, if I just tell you blue, okay? If I tell you sky is blue, okay. But if I tell you has two child, this man, a parent has two children, okay, but we also need the context. Data structures or like real life. This was a definition by Charles Fillmore all the way back in 1976 when he created his paper on frame semantics and the nature of language. So inside our semantic memory, we came with this called the knowledge organization. So as you can see, we have up here, this all from a linguistics perspective, a linguistics domain. So we have an ontology, that's kind of the top level concepts, also grammars and linguistics. Then we have concepts that might be general concepts, like person or dog, or they might be domain specific. And finally, we have something called the speech frames, which, speech frames, which they just store speech, conversation, as pieces of connected nodes. And the graph database that we are currently using is Neo4j. As I was telling you, it has just one constraint to connect self or to nodes. Right now, it's the leading database, graph database solution. It has a community version, and it has an enterprise version. You can download an application local called Neo4j Desktop, but you can also use Docker, or you can even use it with Kubernetes and Helm to deploy it as a service. It uses a query language called Cypher that is actually the main inspiration of something that was just approved as a standard called Graph Query Language, GQL. So keep an eye if you're interested on GQL. So it's also a good idea to learn some Cypher. It's going to be like a natural step for graph query language. It has plugins available, like APOC is just a collection of certain procedures for graphs, graph algorithms, assigning UIDs. You can write your own. They're just small snippets of Java code. You have to put as a jar, but they're really lightweight. As I said, it has a community and an enterprise edition. And yep, that's it.
So